Yeah, we have done about the we have done about the energy in a capacitor. Now we are going to do about the electrostatic energy stored in a capacitor. So within the capacitor, the energy will be in the form of electrostatic energy. Now, what is the amount of electrostatic energy inside the capacitor? Let us derive it. So the derivation is about the energy density. Now, energy density of the capacitor. Now, capacitor will have the energy stored in the form of electrostatic energy that gets again converted into the magnetic energy we will learn in the next chapter. Today we are going to derive the energy density of a capacitor. What is energy density? The energy density is this small u, that is equals to capital U divided by the volume of the capacitor. So the total energy stored divided by the volume of the capacitor. Now if, for example, we are talking about a parallel plate capacitor. Now this is your plus sigma, this is your minus sigma. The area of the plate is A, the separation between them is D. Now, what is the total energy? Total energy equals to Q square by 2C we have done. That is equals to half CV square. Now, this is the total energy. What is the volume of the capacitor? The volume will be area into D. So, AD. Now, what will be the small u? That is the energy density will be half CV square divided by AD, or you can write down Q square 2C by this. So, what will be the answer? Half. What is the C? C is epsilon naught A by D, right? And what is the relationship between V and D? E equals to V by D. So, right? So, you can see here it will be ED. So it will be E square D square divided by AD. So the answer is small u. This is equals to half epsilon naught. This A gets cancelled. D square gets cancelled. So epsilon naught D square. This is the energy density in a capacitor. Right. Now we will discuss about what will be the distribution of the charge in two capacitors, and they are having a potential of V1 and V2. They have the capacitance of C1 and C2. So what will be the distribution of the charge? So if there are two conductors having a capacitance C1, C2, and they are having a charge Q1 and Q2. So what will be the distribution of the charge? Now, when they are brought in contact, then what will be the common potential? The common potential V will be total charge Q1 plus Q2 divided by C1 plus C2. So what is Q1? C1 V1 plus C2 V2 divided by C1 plus C2. Now, when they are distributed, when they are brought in contact, then the common potential is this one. So what will be the charge? It will be, we know that C equals to Q by V, right? Since C equals to Q by V, so what will be the charge now? It will be C1V, and what will be the charge on the second one? It will be C2V. So this is your Q1 dash, for example, and this is your Q2 dash. So therefore, Q2 dash. So what will be the ratio? Q1 dash by Q2 dash will be C1 by C2. So the distribution of charge on two capacitors will be in the ratio of their capacitance, right? So, uh, okay, last one. there is a question that when two conductors having a different capacitance, they are brought in contact, for example. So what will be there? There will be a loss of energy. So there was a question in the board exam that when two charged conductors having different capacitors are brought in contact, there is always a loss of energy. So how to do this? Let there are two conductors having capacitance C1, C2. They are having charges Q1, Q2, V1, V2. When they are brought in contact, then common potential V, this will be equals to C1 V1 plus C2 V2 divided by C1 plus C2, right? Now we know that energy U equals to half CV square. So since initial energy Qy, this is equals to half C1 V1 square plus half C2 V2 square, right? And the final energy equals to UF. This is equals to half the combined C and the common potential V square. Final energy UF equals to half CV square. So what is the value of C? The value of C is C1 plus C2. What is V? V, you know that C1 V1 plus C2 V2 divided by C1 plus C2 whole square. So what is the answer? It is half. Here it will be C1 square V1 square plus C2 square V2 square plus 2C1 C2 V1 V2 divided by C1 plus C2. This is your final energy. So therefore du, change in energy, UF minus UI. So this is UF, so it will be half C1 square V1 square plus C2 square V2 square plus 2C1 C2 V1 V2 divided by C1 plus C2 minus half C1 say C1 V1 square plus half C2 V2 square. Now we are supposed to solve this. Okay. Okay. So du, that will be, take it common. So C1 plus C2, this is your common 2. So it will become C1 square V1 square plus C2 square V2 square plus 2C1 C2 V1 V2, sorry, V1 V2 minus, it will be C1 square V1 square minus C1 C2 V1 square. Then it will be minus C1 C2 V2 square and then minus C2 square V2 square, right? So du C1 square V1 square will cancel, C2 square V2 square will cancel. So if you take minus as common, then it is C1. Okay, we are taking C1 C2 also common, minus C1 C2. So this will be V1 square plus V2 square minus 2 V1 V2 divided by twice of C1 plus C2. So this is minus C1 C2 divided by twice of C1 plus C2, and this is V1 minus V2 whole square. Now we can see here that du is coming negative, right? So this minus sign says that it is there is a loss of energy. Now we can use this formula to calculate the what will be the energy loss when the two capacitors are joined together. Okay,